Hello everyone, my name is Neha and my project is titled Concept Drift Detection and Adaptation in Data Streams using ADWIN for the course Data Warehousing and Data Mining. So in this video, I'll first explain the theory behind concept drift and then walk you through my actual implementation. So now let's begin. So let me start with a question. We have spent the course learning classifiers like naive Bayes, decision trees, random forest. They all work well on training data. But what happens when you actually deploy them in the real world? Every single one of these algorithms shares one silent assumption that nobody talks about, that the data distribution P of X and Y never changes over time. But look at these three examples. A fraud detection model trained in January. By March, the fraudsters have changed their behavior patterns entirely. The model never got updated. It starts missing fraud it would have caught before. And then coming to medical AI systems. In January 2020, every diagnostic model had over 90% accuracy. By April 2020, COVID-19 had changed everything. Those same models failed overnight. And then coming to spam filters. Spammers constantly evolve their patterns. A static filter trained last year will start letting spam through because the patterns changed. So now this is the core problem. The model did not become bad, the world moved and the model stayed behind. So now what is concept drift? So what exactly is a concept drift? Let me give you the formal definition. So concept drift occurs when the joint probability distributions of inputs x and outputs y changes over time. We write this mathematically as p at time t of x comma y is not equal to p at time t plus 1 of x comma y. Simply, the pattern your model learned yesterday no longer describes today's data. Now there are four types. I'll give you one example for each. Firstly, sudden drift. The distribution changes overnight. COVID-19 is a perfect example. One day the data looked one way and the next day everything changed. Secondly, gradual drift. The distribution shifts slowly. Fraud patterns are a great example. Fraudsters don't change everything at once, they slowly adapt their behavior over weeks and months. Thirdly, incremental drift. Very tiny continuous changes that accumulate. Think of how your music taste changes slightly every month. You don't notice it day to day, but over a year, it's completely different. And then coming to recurring drift. The same drift happens repeatedly in cycles. For example, like Diwali shopping patterns, every year in October to November, purchasing behavior shifts dramatically and then goes back to normal. The same drift every year. So let me give you three real stories that makes this concrete. So the first story is UPI fraud detection. NPCI processes over 10 billion UPI transactions every month. Their fraud detection model is trained on historical patterns. But fraudsters are smart. They study the model and changes the behavior every few weeks. A static model trained in January will have significantly degraded accuracy by March. This is gradual concept drift, and the financial impact runs into crores if not addressed. And the next story is Gmail spam filter. You have probably never seen your Gmail inbox completely overwhelmed by spam. That's because Google's classifier retrains constantly. Every time spammers find a pattern that bypasses the filter, an admin style detector catches the drift and the system adapts within hours. Without drift detection, your inbox would be unusable. And the third story is the most interesting one. ChatGPT's knowledge cutoff. ChatGPT has a date after which it doesn't know what happened in the world. That knowledge cutoff is concept drift. The world moved forward, the model stayed at its training point. Every time ChatGPT says, I don't have information after this date, that is concept drift talking. Like the difference between ChatGPT and ADWIN based system is that ChatGPT cannot adapt and ADWIN can. So now let's understand the actual working of ADWIN. So ADWIN stands for Adaptive Windowing. It was proposed by Buffett and Guvalda in 2007 and is now one of the most widely used drift detectors in production systems. So it works in four steps. The first step is maintain window. ADWIN keeps a sliding window W of recent data stream samples. As new data arrives, the window grows automatically. And the step 2 is monitor error rate. It continuously computes the prediction error rate within this window. It splits the window into two sub-windows, an older half and a newer half, and compares them. And the step 3 is half-fitting test. This is the mathematically important part. If the error rates in the two halves differ significantly, ADWIN uses Hofstadter's inequality to determine whether this difference is statistically real or just random noise. If it's real, drift is confirmed. And the step 4 is adapt. The window shrinks old data that no longer represents current patterns is removed. The classifier resets and retrains on the new data automatically. No human intervention required. So this is what ADWIN powerful. This is what makes ADWIN more powerful. It's not just detecting drift, it's mathematically proving drift before acting on it. So now let me walk you through the actual implementation. So in the first cell, you can see that first I installed the River library. This is the go-to Python library for machine learning on data streams. It includes the ADWIN detector, Gaussian airbase, and the electricity dataset all built in. I also installed Pandas, NumPy, Matplotlib library, and scikit-learn for data handling and visualization. Now coming to cell 3, I'm using the electricity market dataset. So let me tell you why this data set is special. It contains natural concept drift. The electricity market conditions in Australia genuinely change over time. And this isn't artificial drift I injected. This is the real data with real drift. And over 45,312 samples, 8 features. The features were date, day, period, NSW price, NSW demand, VIC price, and VIC demand, and transfer. The target label is simply up or down, whether the electricity price went up or down in that half-hour period. Importantly, this exact dataset was used in the original ADWIN research paper by Biffett and Gavalda. So my results are directly comparable to published research. And now coming to cell 3, this is a model without any drift handling. I'm using Gaussian airbase from the River library. The exact same classifier covered in Unit 3 of this course. The only difference is I'm running it on a data stream, one sample at a time, which is called online learning. For each sample, I first predict, then update the accuracy metric, and then let the model learn. And I record accuracy every 500 samples. Now look at the output. So now look at the output. The first output is for sample 500, I got 79.76% accuracy. It looks good, but watch what happens. Now look at the sample 10,000. So the now sample 10,000 has an accuracy of 79.29%. It's starting to drop. Now let's look at the sample 20,000. It has an accuracy of 0.7630, which is 76.30%. It started dropping further. Now let's look at the sample 35,000. So now for sample 35,000, the accuracy is 71.35%. That's the lowest point. Now look at the graph. So the red line is a slow, steady decline. The model peaked at 82.88% and it ended at 72.84%. So that is an 11.53% accuracy drop, not because the model was bad, but because the data distribution changed and the model never adapted. So this is concept drift, destroying a perfectly good classifier in real time. Now let's come to ADWIN. Now what changes when I add ADWIN? The code structure is almost identical to the static model. The key difference is 3 lines. I created a drift detector. Drift.adwin. On each sample, I feed the prediction error to the detector that I mentioned here, detector.update, which updates the error, and I check if detector.drift detected, if whether the drift is detected or not. So when this triggers, I reset the model and retrain from scratch on fresh data. That's the entire adaptation logic. 3 lines. Look at the results. So ADWIN detected 54 concept drifts across 45,312 samples. The very first drift was detected at sample 224, and the accuracy at this drift is 82.59%. It shows how sensitive the ADWIN is. So every time you see an alarm in the output, that is ADWIN catching a drift, resetting the model, and the model immediately beginning to learn the new pattern. And the final accuracy is 88.15%, comparing this to the static model's 72.84%, that is Gaussian naive. So that is a 15.29% improvement purely from adding 3 lines of drift detection code. So now let's look at the graphs. So this is the most important output of the entire project. There are 3 graphs. So the first graph is, it compares the models over time. The red line is the static naive Bayes. You can see it's declining steadily from 82% down to 72%. And the green line is ADWIN. It fluctuates more because it keeps retraining, but it maintains consistently higher accuracy throughout. Now coming to graph 3, the drift detection points. Each red dot is movement where ADWIN detected a drift and retrained the model. You can see them distributed across the entire timeline, 54 of them, showing that concept drift is not a one-time event. It happens continuously in real data streams. Now coming to graph 3, the final comparison bar chart. And the static model shows 72.84%, and ADWIN adaptive model shows 88.15%. The difference is visually stark. Now look at the comparison table. The static model never detects drift and never retrains and degrades over time, and it is not suitable for real-world deployment. The ADWIN model catches 54 drifts, retrains automatically, and maintains accuracy, and it is production ready. And now coming to the conclusion part. Here is a project result summary. So let me show you the final summary output. So the data set is electricity market, and it has over 45,312 samples and 8 features. And the base classifier I have chosen is naive Bayes, and the drift detector is ADWIN. And the static model final accuracy that we have got is 72.84%, and the ADWIN model final accuracy is 88.14%. And the improvement is about 15.29%, and the total drift detected are 54. So now let's look at the key takeaways from this project. So the first key takeaway is static classifier degrades over time. We prove this with an 11.53% accuracy drop on real data. And the second key takeaway is ADWIN detected 54 concept drifts across 45,312 samples automatically with zero human intervention. And the third one is adaptive retraining improved final accuracy by 15.29% over the static baseline. And the fourth one is concept drift directly connects to unit 5 of this course, like data mining trends and research frontiers. This is not a theoretical topic. It runs email, it runs UPI fraud detection, it runs medical AI systems right now. Now I will end with this. Every classifier assumes the words stay still. And the concept drift is the proof that it never does. The question isn't whether your model will fail, it's whether you will know when it does. Thank you.